So good morning, thank you Sharma. We continue with our discussion on cyclic decomposition. Now let us briefly recall some of the ideas that we have explored so far. We assume that V is a d-cyclic substance. Let f be the characteristic polynomial. Now let V belong to V is such that V equal to the cyclic space generated by V. This we have defined earlier. Then what we have seen is that V was here very obvious. E to the power is an ordered basis for which let us designate by V. And what we have is we go for the representation of P with respect to this ordered basis. This is nothing but the companion matrix of now this is something which we have already explored. Then F is also the minimal polynomial of this much information we have already explained. In fact, the characteristic polynomial becomes the minimal polynomial. Conversely, suppose there exists an ordered basis V defined by Vn of V with respect to which the matrix of the solution is the companion matrix of of the minimal polynomial of then P is also the characteristic polynomial of T, and B1 is the cyclic vector that generates that is E equal to in fact Vi becomes for I equal to 1. This is the result that we have already established. Now, our objective is the following. So, what we plan, this is what happens if B is a cyclic space associated with T. Now, our objective is the following. Given T belonging to LB, we want to find non-zero vectors V1, VR belonging to B such that B is equal to that is, this is the breakup that you have, that you want to have. So these are all T cyclic subspaces. Same. T cyclic this is exactly what we are doing. The problem is how to catch hold of V1, V2, etc. Let us explore this problem. So our objective is exploring this problem and then eventually finding out how we can get hold of this V1, V2, etc. Let us do it. Observe that Z is invariable each I. Further, if we write Z B I T prime direct sum of EJB J coming from 1 to R J not equal to R. So let me just J then what do we have? Then what we have is that each ZBIT prime is also invariant under. Okay. That's what we observe. Okay, then what we observe is that each set VIT prime, this is the complement space of set VIT. Okay, to make certain observations. And we also observe that each, ZVIT prime is also invariant. So it's a complementary space of ZVIT, which is also invariant under. Oh, so let us step on. Prime is also and is the complementary subspace of So essentially our problem is the following. Suppose W is an invariant subspace of T. Can you find a W prime with the property that W direct sum W prime equal to V and W prime is also invariant? So the problem is this. So essentially, what we look forward to is given a D-invariant subspace W of V to find a D-invariant V or I will write as D-invariant subspace W prime of V. Such that V is the direct sum of W. Both W and W prime are invariant under. Now this is what we are looking for. We don't know how to catch hold of or how to generate such a space. Now that is one problem. And in fact, we want all those spaces that W prime to be a complementary subspace of W invariant under T, and also can be expressed as the sum of what's called cyclic subspaces. So W prime is called a complementary subspace of B associated with W. That is what we have. So we are trying to find W prime invariant under T given W invariant under T such that V is equal to W plus W. Okay. Now you see that there are several complementary subspaces for W. It's not unique. For example, in R2, you see that this is a subspace. Now there are all lines which are not passing through the origin and are not identical with W is a complementary subspace. But what we are looking for, if the W is invariant under T, they are all related to T. So W is invariant under T, and you want W prime to be a complementary subspace as well as something invariant under T. Now this is our task. So there are several complementary subspaces that you can have, but we want a complementary subspace which is invariant under. That's the problem. Now let us explore this. How do we try to explore this problem? Do some initial problem. before we write down the final theorem, and then a little bit look at this. This theorem is very fascinating, but its proof is very large. So let's say just but anyway, let us explore this. So our objective is very clear at this stage. We are going to. So we work backward and get some insight into the problem. That means if there is such an invariant subspace W prime and V is equal to W plus W prime, then what all things happen? Because they are all related. So let us work backwards. Now this is often a technique that we very often use in mathematics. What does it mean? We assume that this kind of thing happens. That means, and then we explore what are the consequences. Okay. Suppose W is an invariant subspace is a T-invariant subspace B and W prime is a complementary T-invariant subspace. That is B is equal to W plus W prime T W W. Then B belonging to B has a unique resolution. Right? W belonging to B now this is a unique resolution of B. Okay. Now take any F not necessarily the characteristic polynomial. The polynomial algebra associated with F. Then what we have is TW is contained in W, TW prime is contained in W. So what we can assert is that Ft of W is contained in W right? You also have Ft of V So for f belonging to fx, this is true. Now the consequence of this is the following. Ft of v equal to Ft of w if and only Ft of w is equal to 0. This is true for LDF. Okay. That is FTW FTV belongs to W and only and that is if and only if this is what we do. Now this observation allows us to introduce a new concept of T-ethnicity. Let us introduce the new concept that is called T-ethnicity. So let us now introduce T-ethnicity. T-ethnicity. Then we say that W is T-ethnicity if the first condition is that W is invariant. The second condition is that if Ft belongs to W, there exists W belongs to W such that So that FTW prime is equal to 0, and that is equal to the existing prime such that V equal to W plus W prime and FTW prime equal to 0. Okay. Hence, what we have is this. The conclusion is that in terms of this new terminology, hence the ring T invariant has complement subspace which is also T invariant. If and only if W is that is FTV equal to FTV belonging to W, or this P admissibility actually characterizes the T invariant subspaces having complementary invariant subspaces. That is T admissibility of W characterizes the existence of characterizes the class of T invariant subspaces having a complementary subspace we have made the existence of such pair W and W prime a bit more transparent. Okay, so it has been condensed into the concept of what's called P admissible, W being admissible. Okay, so the question is this. This is our basic question. How do we use this exploit this idea in getting a cyclic decomposition? So this is our basic problem. This is where we start with. So let us assume that, so we are attempting to determine B1 such that B equal to so we do this through a type of induction algorithm. So let Wj then we want to find out Ej plus 1 such that then we get W is 1. This is the strategy. Okay, so we get W is, and then we repeat that. Use the same technique to identify Ej plus 2, etc. until you exhaust the whole thing. The whole entire V is exhausted. Repeat the process. That is what we have is that Wj plus 1 is properly calculated here. Or what we call Z. This is like what I wrote in right. Is it? I start. Otherwise, you stop. Lost. After all, it's a finite dimensional spaces. Therefore, the process has to terminate in finite number of steps. So, since we are working on finite dimensional spaces, the process has to terminate in finite number of steps. So, that's what we have. So, let us explore this idea. First fix these ideas and then proceed to write down. Then the proof is love. So we break it down to 8 steps. Yeah. So what's the question now? The question is, these are our class. So once you do that, so we have cut out the strategy. The strategy is we use a type of reflection. So let's take some clarity. Okay. So let us explore this one. Let W be a proper substance. We want to find a V belonging to V. Because V dot such that this is how. So that's the problem. Let us see how we work on it. Suppose this is here. Suppose this is here. Now we have to pick the particular V which helps us. Okay. So we start with an arbitrary element U belonging to V, but U not in. Okay. Now look at the T conductor of U into W. This is not empty. Why it is not empty? because at least it contains the characteristic polynomial of U. Okay, because it maps every vector to 0, therefore in particular U is also mapped to 0. So there are plenty of such polynomials for which ft of U is in W. Okay, right? So let us make note of this part. And then we use the property of W or the assumption that W is T-admissible. Okay, right? So if W is T-admissible, then this is what happens. This is which is inside W. Now, what T-admissibility tells is that there is some W here such that this is also equal to T-admissibility assures that there is a W such that Ft is equal to Ft W. Now look at, consider the vector V equal to in that case what happens? FTV equal to FTU minus FTW, but FTV, FT, this is it. But FTU equal to FTW, therefore FTV equal to. So this is the 0 element. Okay. Then FTV equal to 0. Okay. So we got a vector outside the pool which gets mapped to 0. I mean, this is how we manufacture that anyway. And there we make use of the property of the admissibility of the. Okay. So once you get that, the process is this. You look at the cyclic space generated by V. The cyclic space generated by V in that case, that is ZVT, will have only the 0 element common to it, W. Therefore, and also the ZVT has the property that it is going to be invariant under T. Okay, and then you see that W direct sum ZVT is W is say W prime or something like that, and that also has the same property as of the admissibility. If so, we can continue this process. So this is the study. Okay. So let me just point out the following. Start with an arbitrary U, which is not in W, but in V. Then you see that FTU is in W, provided Ft is the T conductor, is a T conductor of U. Right, you have the whole class of T conductors. One is the whole class. Okay. So let's find out those things. So I think the picture should be clear. started with a proper subspace of V. We want to find out a V belonging to V such that V does not belong to W and W intersection Z into is zero. So to see, the whole problem is our objective is to find this V. And finding this V, hitting upon the right V is not that easy. Maybe in the computation, this case problems if you come. If you are computing, it's quite easy. It's not difficult. We shall just look at some problems later. But in general, see that's not difficult though. But we are now giving a procedure. After all, since W is properly contained in V, there exists U belonging to V, but U does not belong to W. Okay. Now consider the D conductor is the whole class of which we designate by S. Which is defined as a set of all F belonging to X with the property that Ft of U. Now you know that this is an empty. Okay. This is an empty. And has a temperature. This designated frame F, which is defined by S V. That's our definition of this. Now, this F is also called the E conductor of U. Because it identifies, it generates a single polynomial that does identify every F having this. So we have what we have as this FTV. If W, now we use the fact that W is clear. If W is clear, then there exists W belonging to W such that Ft of W that is just the application of that of the definition. Now define you refer into the diagram. Now define this is the definition of U by this. So we started with a U, identified the W, but there exists a W, then U minus W becomes this. Okay? Right? Then what is Ft? So V is the vector with the property that Ft is 0. Now what you can prove is twofold. So what one can prove is that yes. W is the same as that's quite easy to do. Start with an S, V, W. Show that it has the property that it is an element of S, V, W. Start with an F, okay. F is in the P, and there is a U corresponding to this. U has been constructed accordingly. You will start with an arbitrary G belonging to this. And what can you say about G? G is a polynomial multiple of F. Okay? So G belonging to this is a polynomial multiple of F. And then you see that this G has the property that G of okay, we start with the V. Okay. So you start with something here and then you show that it's okay. It's a multiple of F. So G is a multiple of F. So G belonging to yes. Now what about GB? Which is equal to H of and FTU equal to FTW, therefore this is equal. See, so you see that every element of this is an element here. And you reverse argument and then you get that. So that's quite easy. So once you prove that, once you identify this, so this, so you have for every G belonging to S. Belongs to W, which is defined only GT of Now, what is the consequence of this? So, you look at the definition of Z. What is ZPT? ZPT is essentially okay. So for every G belonging to S P W, you have GT V equal to 0. Okay. Therefore, the common element of W and therefore W intersection Z this is what it is. Okay. That means look at the definition of both. The beam has the property that GT V is unique. Okay. At the same time, you know that GT V is equal to 0. Okay. Right? Therefore, the common element of so what we obtain is this W intersection so any element of W which is common to ZBT has the property that this is equal to C. Therefore, you get the element of ZBT is equal to 0. So the common element of W and ZBT is 0. So the whole picture emerges with this. You have V. Now this is already there. There is the 0 element. Now what we do is we start with a U. U is mapped into then you have a V, a W, which is also mapped into same element. So this is equal to W. Now choose V. Choose V such that V is equal to then what happens is that this is the one that gets mapped. Okay. Now you choose this V and then form what is called so you see the only common element between ZBT and W is the 0 element. Okay. So eventually what happens? Okay, let us look at that. Let us look at the figure that emerges eventually. What is this? Lava. This is good. This is the zero. Suppose you have found a then what you do? Find a V2. Find a V2 outside this such that if they do not add up to V, then what you do is find a V3 and then generate and so on. Eventually end up with the VR in between you have these leaves coming. All of them have zero in common. So these are all invariant subspaces and so on. So you have Z is equal to or V equal to this is the whole strategy of working out this. Okay? So we have decoded what is going on. Get set V1, find V1 somehow, get set V1 T. If that does not fit V, then you get a V2 outside Z V1 T, construct Z V2 T, and then look at the direct sum of these two Z V1 T and Z V2 T. If it is not equal to T, not equal to V, then go ahead constructing V3 and so on until you get all the V1, V2, etc. VR such that the direct sum of these cyclic spaces will be the mole of V. Now this is the strategy. Okay. So we have roughly given our plan, right? And our next task is essentially to go about constructing this, and this is done in the cyclic decomposition. So I will start with the cyclic decomposition here and prove it in parts because it's a longish proof. So we will do it in probably 2 or 3 lectures. Thank you very much.